day one. Now, because this is fourth period, because this class is over a lunch period, we never get screwed up by a late start day. We will never get screwed up by a late start day, which is really nice. Because I never have to worry about that. Like tomorrow is a late start day, but we have a full period tomorrow. Your classes during the lunch periods do not get changed, which is really nice because I was thinking, like, when I saw it was a late start day, I was like, oh man, we're going to have to do 3 days on this section. And we're not going to have to. I'm going to be able to finish these notes tomorrow, and you're going to have some time to work on your homework in class tomorrow. Okay? And it all kind of depends. I might do a work day over section 2-3. I might, if we see how we're doing on this, I might do it just over section day 2, or sorry, section 2-2. It just kind of depends. I really want to keep it fluid with you guys. All right, so again, we're in this side, like figuring out what a limit is, right? We kind of introduced it yesterday with the tangent and velocity problems. But now we're going to be looking at it a little bit more algebraically and trying to find a precise definition of a limit. And what do I mean by that? Or like we're going to be finding rules on how to calculate limits. Because if we can do the mathematics behind limits and actually operate with limits, we can then do some really cool stuff with finding instantaneous rates of change and things that are happening right now on curves. All right, so having seen the preceding section, how limits arise when we want to find the tangent to a curve or the velocity of an object, we now turn our attention to limits in general and numerical and graphical methods for computing them. All right, let's first investigate the function x squared minus x plus 2. A simple parabola, right? If I were to graph this, it would not have any real zeros. It would just be above the x-axis, y-intercept of 2, pointing up, all those things that we've learned in Algebra 1 and Algebra 2. What if I had said, I want to calculate the value of that function as the function approaches, as the x value approaches 2. Let's take the x value of 2, and let's see what's happening to the function as I approach 2. Now, what we did yesterday was just kind of the plug and chug method, where we just say, okay, well, let's find numbers close to 2, and just keep getting closer and closer to it to see what the function would lead itself to be. So that's all you see in this example here. I'm taking 1 and then 1.5 and then 1.8 and then 1.9 and then 1.95. And all I'm doing for that function is just plugging in those values to see what the y value would turn out to be. I'm plugging in 1. I'm plugging in 1.5. I'm plugging in 1.8 and so on and so forth. And we see it goes from 2 and it keeps getting closer and closer to, what do you think? What do you think it's getting closer and closer to? 4, right? We just make that observation. We think it's going to go to 4. It's going to be very important, especially today, that not only do we check the lower boundary, but we also check the upper boundary as well. Like we go from 1 up to 2, but we should always check the other side of the limit as well. We should check going from 3 and then reduce the number to get down to 2 as well. Like, so we take 3 and then 2.5 and then 2.2 and then 2.1 and 2.05 and 2. And so on and so forth. It's a little bit labor intensive. So we calculate and calculate and calculate. And what do we see from the other side as well? That it equals 4. Let me ask you a question. What would be the value if I just plugged in the number 2 into this equation? 2 squared is 4. Minus 2 is 2. Plus 2 is 4. So you mean to tell me if I just plug in the number, that's what the limit equals? Most of the time, yeah. The issue arises is when we cannot plug in that number, which you'll see here in a little bit. From the table and graph of the parabola, we see that the closer x gets to 2, the closer the function gets to 4, the closer the y value gets to 4. In fact, it appears that we can make the values of f(x) as close as we'd like it to 4 by taking x sufficiently close to 2. That phrase gets used a lot, sufficiently close to. What we're doing there is saying, okay, we've made it close enough to the x value that we want to get it to, that we can make an observation, a pretty sound observation that yes, it is actually going to get there. Yes, we believe that it's going to get there. We believe that it's going to get to 4. Here's how we write this. We're taking an easy example that we can plug in to show you what the notation would look like. This is the notation that we're going to be using. Okay? Let's read this notation. The limit as x approaches 2. Okay? The limit, and usually for our notations, and I'm going to show you a couple different types of notations. The limit as x approaches 2, meaning as I make x closer and closer and closer to 2, from both sides, as x gets closer to 2, as x goes to 2, of, and we always put the function in there. So we're saying the limit as x goes to 2 of this thing, we looked at it graphically and plugging in numbers. The limit as x approaches 2 of this function is equal to 4. That's the notation that we read here. Okay? In general, we use the following notation. So how do we expand on that? How do we generalize that? Well, we say the limit as x approaches a, and a is always some value. The limit as x approaches 2. The limit as x approaches 3. The limit as x approaches 0. The limit as x approaches infinity. We will do that as well. As x gets really, really big, what happens? Or as x goes to negative infinity. As x gets really, really small, what happens? Of the function, right? The limit as x approaches a of f of x is equal to some number L, right? And we use a capital letter when we're just generalizing it. We're saying, okay, some number L, the limit is going to equal that number. For example, the limit of x approaches 2 of that function was 4. So the limit was 4 of that function as x approaches 2. You always have to be very careful to say what the limit is going to go to. Like the limit as x approaches 2. You can't just say the limit of the function is 4. That doesn't really make sense. What does that mean? That means that the limit as x gets closer to 2. You have to specify where your x value is going to say where your y value is going. Okay? And this, again, is how we read it. The limit of f of x as x approaches a equals L. Okay, some other types of notations that you might see. This is a notation that is sometimes used in the book as, and sometimes it's switched around too. F of x approaches L as x approaches a. Okay, this is saying like, okay, the function x squared minus x plus 2, I think it was, approaches 4 as x approaches 2. Right? That's how we would read that. That's how those translate. More often than not, I mean, I got to be honest, 90% of the time we see it written in this notation. 95% of the time, probably. Okay. I wanted to show this to you as well. This is a more like inline method to use. Like sometimes when if you see it in books or something, you don't see any x approach a underneath the limit, like just so it fits in within a paragraph. So if you ever see it like that, that means the exact same thing as well. Okay. Okay, now one last thing I want to talk about before we get to an example. Yeah, one last thing that I want to talk about is, did we really need to plug in the value of 2 into that parabola? Did we need to plug in that value of 2 to figure out the limit? No. All we were looking at was things around 2. We didn't actually care about what was actually happening at 2. We only cared about the things around it and made a decision about the limit based on the things that were happening around it. So that actually means that the function could actually be undefined at that certain value to be able to tell the limit. Okay? And that's a very important concept. The function may not be defined at that value to be able to determine the limit. Like for example here, the limit as x approaches a of this function, some weird wacky function that curves a bunch of times, as x approaches a, looks like it's defined, right? There's not like an open circle. But if I change that up, does that change anything? No, because what's happening around a? It's still getting closer and closer to L from this side and that side, okay? Even though it's an open circle. Even though it's an open circle and it equals something else. Look, there's a closed dot down there. Even though the function equals something completely different, the limit could still exist at that place because all I care about are the things around it, right? It may not be defined at all, right? This one, it was defined. It was like a closed dot somewhere else. This, it may not be even defined at all. This is an open circle with no closed dot. Maybe it could even go to infinity. Maybe there could be an asymptote or something happening where it wouldn't be defined. It doesn't mean the limit is undefined. Okay, that doesn't mean the limit does not exist. So take, for example, this. I love this. Guess the limit at. Okay. We're just going to guess. I don't know. I guess. Guess the limit. Guess the value of the limit as x approaches 1 of x minus 1 over x squared minus 1. Now, maybe we can do that whole plug it in thing. What would happen if I plugged in 1? What would happen with this function if I tried to plug in 1? It'd be undefined, right? Like this would be 1 minus 1 over 1 squared minus 1. That would be 0 over 0. That would be undefined, right? I cannot divide by 0. So this is a case where, this is a case where that limit does not exist. Or sorry, that's not true. The limit is not possible to calculate if I just try to plug in that number, like it was the first time. Like I could plug in 2 into that parabola and I just get out 4. I can't do that here. So what's the next best method? Well, let's plug in things around 1 and see what happens to it. Let's plug in things around 1. So let's do that. Maybe we start from the short end and go with 0. What if I plug in 0? Now I'm going to very precisely write this out here. Okay, I've got 0 minus 1, because I want to copy this in, divided by 0 squared minus 1. Okay, so if I plug in 0, I get 1. Well, let's get closer. Let's get closer to 1. So let's say, instead of plugging in 0, I'm going to plug in 0.5. Okay, let's plug in 0.5. Okay, 0.5 minus 1 divided by 0.5 squared minus 1. Okay, we're getting somewhere. Okay, let's do the exact same thing. Let's get closer to 1. Let's go all the way to 0.9. Oh, whoops. 0.9 squared minus 1. Ooh. I go from 1 down to 0.6, down to 0.53. Based on this, do you think you can make an estimate? Do you think you can make a guess on where the limit's going to be? Maybe we should run one more number. Maybe we should get just a little bit closer to 1. Let's do that same thing, but now instead of just 0.9, let's do 0.99. Just to get it a little bit closer to 1. Do you think you have an estimate now? What do you think the limit is going to go to? 0.5. Should we check the other side too? We should. I'm going to be a little cheater bonita here, because I have all the tables here for us. Take a look at what's happening. Look, they didn't even plug in 0. They just went straight to 0.5. They went 0.5, 0.9, 0.99, 0.99, 0.9999, and so on. And look, they did it from the upper side too. 1.5, 1.1, 1.01, 1.001, 1.0001. Do we see it a little bit clearer now? Do we see that the limit looks like it's going to go to 1/2? Yeah. You guys want to see something cool? Cool in my opinion. This is like the math cool. Okay. Let me move this down a little bit. If I do x minus 1 over x squared minus 1, guys, what does that factor into? X squared minus 1? X plus 1, x minus 1, right? What happens to the x minus 1s? They cancel. So this ends up reducing all the way to this. So if we actually want to, the limit as x goes to 1 of this 1 over x plus 1, could we plug it in now? Can we plug in 1 now? Yeah? You see that? So even though we couldn't plug it in before, even though if 1 gets plugged in at the very beginning, 1 is undefined. There is a hole in the graph. There is a hole in the graph at 1. even though 1 is not defined, the limit still exists. The limit still exists, even though 1 is not defined within the graph. The limit still exists at 1/2. And you can calculate it if it reduces down. Now, this is a unique case where it reduced down and it was nice and rainbows and unicorns, but everything isn't like that. Okay, this was just a unique case that it could reduce down, and then we were able to plug in 1. Okay, so let's take a look. Okay, so what if we shift this example a little bit and said, okay, what if we define 1? What if we say, okay, now I'm going to make the x value 1 equal something weird. Make it equal 2. Does that change the limit at all? Does it change the limit if I say, okay, if I want to know what the limit is as x goes to 1 of this, oh, they called it g of x now, of g of x, does that change the limit? Even though I'm making the x value of 1 be a weird number, something odd, or something totally off the wall, I say, okay, if x is 1, the function equals 2. This weird piecewise function where we say, okay, let's make it something really weird. Let's make x equal 1 come out to be 2. There's still a hole in the graph here with that same example, right? You guys all see the hole there? There's a hole in the graph. Does it change the value of the limit? No. It does not change the value of the limit. Because if I plug in numbers close to 1, it will give me the exact same tables that I had down here, right? That's the exact same thing. Nothing would change if I get close to 1 from either side. So the limit is still 1/2. The only difference is if I go to the function, when I plug it in, it may not be that answer anymore. See, this is that weird case where could I plug it in now anymore? No. I've actually switched the value to be something completely different. Okay? Switch the value to be something completely different. So it's going to be very tricky how we define, how we calculate limits. So that whole plugging in rule works some of the time, but not all the time. You got to be very careful when you apply it. We'll learn rules about that when we get to section 2-3. Okay, so let's take something else weird. This weird square root thing that we got here. And let's guess at the value of, and let's understand the notation because that's kind of half the battle here. The limit as t approaches 0. So I'm going to get t closer and closer and closer to 0, sufficiently close to 0, to see what happens with that function. What happens with the outputs if I get t closer and closer and closer and closer to 0? All right. Now, I'm going to have to be very careful how I plug this in. Okay, I've got the square root of t squared plus 9. Let's start at like 0.5, shall we? I'm going to go 0.5 and then go down to 0. I'm going to start on the upper end this time. I started on the lower end last time. We'll start on the upper end this time. So let's go 0.5. 0.5 squared plus 9. And my parenthesis for my square root. And then minus 3. Oh, you know what? I have to put this whole top in parentheses. I got to go all the way up here. The whole top in parentheses. Divided by, and then I've got 0.5 squared. T squared. So I'm going to plug in 0.5. Now, I should have prefaced this. Are we able to just plug in 0? No. That's why I'm doing this whole process of narrowing my focus down to 0. Because I can't plug in 0. At 0, this function is undefined. There's a hole in the graph somewhere in it. I don't know what this weird, wacky thing looks like. But I'm going to start with 0.5 and see what happens. Okay? Well, that doesn't make any sense to me. Let's just plug in another number. See if it leads to something. So maybe let's go to you want to go to 0.9? You want to jump to 0.9? Let's do that. My calculator's slow. It's laggy. 0.9. Okay, so it got smaller. Oh, shoot. I'm not going to 0. I'm sorry. Remember, I'm starting on the upper end. that was a bad idea. I went to 0.5. I got to go down to 0. Look, this is the limit as x approaches 1. Whoops, sorry about that. So I got to go back in here. I don't want to go up. I want to go down. I want to go down towards 0. So instead of going to 0.9, let's go to like, we have 0.5. Let's go down to 0.1. Because we're trying to get down to 0. Not up to 1. I did it the wrong way. Okay, here we go. This is much better. So I was at 0.165. Now I'm at 0.1666. Ooh. Let's do that again. But now let's say, okay, what if I go to point, insert a 0. 0.01. Try the same thing over here. I want to go here. Insert a 0. Okay. Is it leading to something? 0.16 repeated? Anybody know the value of 0.16 repeated? Not 2/3. That's just 0.6 repeating. This is actually 1/6. 1/6. This is actually 1/6. Now, I am doing this example specifically because when we get to section 2.3, we algebraically find how this is going to be 1/6. I can't tell you yet. I can't let the cat out of the bag. But for right now, all we're saying is, okay, it's going to keep getting closer and closer and closer to 1/6. 0.16 repeating. It's getting closer to 1/6. Okay? Soon we will learn how to do this algebraically. They're showing the plus or minuses in there because I just checked the upper side. I just checked from 1 down or 0.5 down to 0. But look at what's happening within the function. Does it matter? Oh no, I've got a t squared. So plugging in 0.5 is the same as plugging in negative 0.5. Plugging in 0.1 is the same as plugging in negative 0.1. I feel like I'm back in 7th period. Alex is sleeping on my sleeping during the class.
I'm mostly.
It's all soaking in somewhere, right?
Yeah, I got my notes down right here.
Okay, yeah. All right. And you passed algebra 2, so I'm hopefully staying out. Right?
I'm here.
Present in class. Okay, now, in example 2, what would have happened if we had taken even smaller values of t? Now, this is where it gets to start to get really weird. If you thought that was weird, okay. In example 2, what would have happened if we had taken even smaller values of t, made it smaller and smaller and smaller and smaller? Look at my table. We went to 0.01 in our calculator, but look at what would happen if I keep going? It actually goes away. Why is that the case? Well, your calculator only calculates so many digits. And what it's doing there is it's saying it got close enough to 3. It got close enough so that inside here went all the way to 0. That t squared plus 9 went all the way to 0. Like it actually became negligible. And when that happened, it made the whole thing go to 0 as well. Okay? So your calculator is going to lie to you sometimes. Your calculator is going to give you weird answers that don't actually make sense. The problem is that the calculator gave us false values because it got so close to 3 when t is small. Okay? This happens a lot. If we were to actually graph this and we were to zoom in and zoom in and zoom in on the axis, look at what happens to the graph. Something goes really haywire with the equation, and it just goes nuts up right in the middle there. If you were to keep it zoomed all the way out, you wouldn't even see that. But if you got closer, look, this is going just with the x values of 10 to the negative 7th, or negative 10 to the negative 7th and positive 10 to the negative 7th. So really, really, really zoomed in, that's what it looks like really close to the axis. Isn't that weird? Like just so weird that that's actually happening there. Why? Because t can never equal 0. T can never equal 0, but it's going to get closer and closer to 0 that you can calculate what the limit would actually be. Okay, we're going to see this here again in a second. Let's guess the value of the limit of as x approaches 0 of sine of x over x. I want you guys to fool around with your calculator a little bit. Try to figure out what it's going to be. I want you to go through the process of just plugging in some numbers. and see what it would turn out. First of all, can I plug in 0? No, I can't in this one because I've got over x. And if I just plugged in 0, it would give me a no solution, right? It'd give me an undefined. So go ahead. Maybe plug in 0.5, plug in 0.1, plug in 0.01, plug in 0.01. Maybe it might be a good idea to go from the other end as well. I'll give you a minute. This is what you have to do a lot of times on your homework. Just to make sure you know how you can do it. Anybody see a pattern? Anybody want to guess what the direction here? Guess at what the limit's going to be? I don't know. My math brain in me is like, when I hear the word guess, it's like nails on a chalkboard. It's like, oh, okay. I hate guessing. Anybody got a good guess though? What do you think? I would agree with you. Let me show you the table that I have here. As I keep plugging in numbers close to 0, if I keep plugging in numbers close to 0, it's going to get closer and closer and closer and closer to 1. Sine of 1 over 1, 0.84. Sine of 0.5 over 0.5, 0.95. And I keep going and going and going and going and going and going until I get this idea of being sufficiently close. Sufficiently close enough to see a pattern. Yes, sir.
Am I in radians or something?
Well, let's check it. I think you want to be in radians and you are in degrees.
Okay.
There we go.
Awesome.
Yeah, maybe check your calculator. You should be in radian mode. If you're not, then this is getting weird. It's getting like a 0.1 or something.
Thank you.
Makes so much more sense now.
Yeah, we should have like sine of 0.01 divided by 0.01. Let's make sure my calculator's in radian mode. Yep. Yeah. Okay. So that's our process right now. That's unfortunately the only way we know how to find limits right now. Is to just run the numbers. Is to just do the math. Just plug and chug. Okay? All right. Now, this next question, I'm going to investigate again. I'm just going to see what's going to happen with sine of pi over x. Sine of pi over x. Let's change that from sine of x over x to sine of the whole pi over x. First off, can I just plug in 0? No, I can't, because x is in the denominator. So if I try to plug in 0 into the denominator, this function is undefined at 0. So if this function is undefined at 0, let's try to investigate what's happening around 0. Now, take a look at the x values that I chose here on the board. What if I plugged in 1? Well, that would be sine of pi over 1, so sine pi is 0, right? Okay, what if I plugged in 1/2? Well, I'd take the reciprocal. Sine of pi divided by 1/2 is sine of 2 pi. And sine of 2 pi, the y value of 2 pi, is 0. What about 3 pi? What if I plugged in 1/3? That would be sine of 3 pi. So on the other side of the axis, but still the y value is 0. What if I plugged in 0.1? Okay, so that's sine of 10 pi, which is full rotations, get us back around to 2 pi, the y value's 0. What would you estimate the limit to be then? What do you think the limit's going to be? Now this is the one that's a trick question, because it's not actually 0. Take a look at what happens to the graph. See, the calculator is going to lead you into thinking that it's going to be 0. But I had just strategically picked x values to make it turn out to be 0. There are all sorts of different x values. I just plugged in ones that came out to be pi or 2 pi rotations. So my y values kept coming out to be 0. But if I had plugged in any other number, it would have gotten me any other possibility between -1 and +1. Now, let me ask you this, seeing this graph, as I get closer and closer to 0 from either side, does the function actually narrow to anything? Does it narrow to one number? No. It's going to keep waving and waving and waving. I could zoom in and zoom in and zoom in and zoom in and zoom in, and it would just keep waving. It would just keep going up and down and 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 up and down with no convergence, right? It's never going to converge to one number. So what do we say about this? We say that the limit of that function, our true answer is the limit of as x goes to 0 of sine of pi over x does not exist. The limit does not exist. That's what we say when it does not converge, when it does not go to one number. If the limit does not converge to a singular number or does not go to infinity, then we say the limit does not exist. Okay, the limit does not exist. The reason it does not exist again is that it does not go to one number, right? It does not condense down to 4. It does not condense to 0.5 or 1/6. It does not go to anything repeatedly. It just keeps varying. So we would say that the limit does not exist. Okay. I want to just show this example too. We could run the numbers here, but again, I think we've done the process. We know what we're doing in that respect. But I think this is interesting here. Take a look at what happens if I plug in 1, 0.5, 0.1, 0.05, and 0.01. What do you think the limit is going to be? What does it look like the limit is going to be? I mean, in my mind, I'm like 0, easy, right? Looks like the limit's going to be 0. But if I just go 2 more spots on that table, if I just keep going a little bit more, whoa, what is the limit now? 0.0001. And we see it now. Look, we just hadn't seen it converge yet. We were going down to 0.001, and we were like, oh, it looks like it's going to just keep disintegrating, right? But if I had just gone 2 more steps past that, if I had just gone to 0.005 and 0.001, we would have seen that it actually converges to 0.0001. Now, the interesting part about this one is, what is 0.001? 0.0001. What is that equivalent to in fraction form? Well, that's tenths, hundredths, thousandths, 10,000ths, right? We're going to see, look, do you see any relationship between that? We're going to find, this is another example that we're going to hit later again, once we learn the algebraic methods of solving limits, that this is actually going to converge to 1/10,000th. We're going to find that the limit as x keeps getting smaller and smaller and smaller and smaller, as x goes to 0, that's going to go to 0. That's going to get canceled out, basically. And then this is going to go, we're going to see that cosine of 5x converges to 1. And then we're going to say, okay, since cosine of x converges to 1, this whole thing goes to 1/10,000. Okay? But then again, that's for later on. Okay, that's for later on. Because now we're going to get into one-sided limits. Let's pause here. I feel like we've learned a lot today. We've done a lot today. So let's just pause for the day here. We'll pick up with one-sided limits tomorrow. Sound good? Sounds good to me.